In this video we're going to consider the absolute value function, or sometimes called the modulus function. And we've actually come across this notation in quite a lot of contexts already, so with vectors and matrices and complex numbers, but we haven't really thought too much about it just in relation to numbers or algebraic expressions. So we're talking about functions which contain the absolute value operator, or the absolute value, or the modulus operator. So expressions like the absolute value of 3 would be sort of one of the most simplest cases we could consider. When we think about the absolute value of an expression, we're saying the size or magnitude of that expression, and so the absolute value of an expression is always greater than or equal to 0. So when we say what's the size or the magnitude of the number 3, well, it is in fact just 3. Now, one of the ways that we can think about this, probably in simpler cases, which might help us to be clear on the meaning of the absolute value operator, is to think about the distance of a number from 0. So if we're saying what's the absolute value of 3, we could draw ourselves a number line here and say, okay, there's 0, number 3 maybe sitting about there. We say, what's the distance of that number from 0? Well, its distance is 3 units. So what about then if we considered another example, like the absolute value of negative 9.2? Well, if you think about where negative 9.2 is on the number line, let's say it's somewhere down here, and we say, what's its distance from 0? Well, its distance is 9.2 units. So we're not talking about displacement here, just its distance. How far away is it? And so we say it is 9.2. So like I say, the absolute value of an expression is always greater than or equal to 0. And so in sort of these really simple cases, we can say, well, if it's a positive number, then the absolute value is just going to be equal to that number. And if we're talking about the absolute value of a negative number, like negative 9.2, then we're saying its absolute value is the negative of that, which is positive 9.2. So in some ways we could say positive numbers are unchanged by taking their absolute value, and negative numbers have their sign reversed by having their absolute value taken. So we could try and define that perhaps a little more formally. So we could define absolute value as follows. The absolute value of x is equal to, and it's going to be one of these kind of multi-domain functions. So it's going to be equal to x wherever x is greater than or equal to 0. So as long as that term in there, that expression in that value of x is greater than or equal to 0, then the absolute value is just the value of x. But if this thing in here, the value of x is negative, then the absolute value of that will be found by taking the negative of that. Does that make sense? So if x is a negative number, like negative 9.2, then taking its absolute value means it's going to be equal to the negative of negative 9.2, which is positive 9.2. So what does the graph of the absolute value function look like? So here we could sort of actually consider it as a function rather than just as an operator. So we're talking about the function y equals absolute value of x. That would be the simplest case that we could consider. Let's draw ourselves some axes. Now, because the absolute value there is always going to be positive, on the positive side of the x-axis, so for values like 1, 2, 3, 4, and so on, the absolute value of x is just equal to x. So in other words, y is going to be equal to x for all of those. So if we just consider those integer values, so on this side of the y-axis, that's just going to look like y equals x. That's because the absolute value of x is equal to x for positive values of x. On the other side of the y-axis, it's going to look like y equals negative x, which is this one here, isn't it? So on that side, so when x is negative 1, y will still be positive 1. When x is negative 2, y will be positive 2. When x is negative 3, y will be positive 3, and so on. Now, we're just talking about integer values there, but obviously it applies to all other values of x as well. So that gives us the graph of y equals the absolute value of x. Now we can consider transformations of that. So what happens if we add or subtract something from that? What happens if we add or subtract something to x inside the absolute value before we take the absolute value? So they're things that we'll need to consider. But what also about just working with expressions like this, if they're algebraic expressions, and solving expressions which involve absolute values? So let me consider a couple of questions like that. And these ones here, we're wanting to solve for x. So here's an example. We can say the absolute value of 5x minus 3 is equal to 9. Okay, the absolute value of 5x minus 3 is equal to 9. Now, if you think about the way that works in an equation, in an equality statement, then really, as long as what's in the brackets there, not in the brackets, what's in the absolute value operator there, as long as that expression 5x minus 3 is either equal to positive 9 or negative 9, then its absolute value will be equal to 9. So there's actually two cases for us to consider there. Does that make sense? So as long as 5x minus 3 is either positive 9 or negative 9, then its absolute value will be 9. Now, I'm going to express it slightly differently, and that's because when it comes to inequations or inequalities, this is going to be important. So let me state our two cases. And when we're sort of showing working out for these, it's actually worth putting these down. So we've got case 1, and then over here I'll say case 2. So case 1 would be where the thing inside the absolute value is positive. So I'll write it down in this case. We don't really need to write this, but this would be where 5x minus 3 is greater than or equal to 0. And the second case would be where 5x minus 3 is a negative number, where it's less than 0. So in that first case, well, if 5x minus 3 is positive, then taking its absolute value doesn't change it at all. Alright, so 5x minus 3 is 0 or positive, then applying the absolute value operator to it does nothing to change it. Whereas in the second one, if 5x minus 3 is negative, then applying the absolute value operator to it makes it the negative of 5x minus 3. So think about that and make sure that makes sense. Because 5x minus 3 was a negative value, applying the absolute value operator to it makes it the negative of what it was. And so it's now positive. Alright, so solving these two cases here, we get 5x equals, what's that, 12. So therefore one solution would be x equals 12 over 5, or what's that, 2.4. And the other solution here would be when negative 5x equals, what's that, 9 minus 3 is 6. Therefore x is negative 6 on 5. Now, like a lot of algebraic work, of course, it would be worthwhile, if we're not absolutely sure, it'd be worthwhile just subbing both of those values of x into the original equation, the original expression, and just checking that they do both provide solutions. But both of those are solutions to that. Now, what about, let's consider one where we've got an in equation And the way these are expressed are a little bit different here. So this is saying find the set of all values of x such that the absolute value of x is greater than or equal to 5. That's a fancy way of saying find the solutions, all the solutions to absolute value of x is greater than or equal to 5. Because this one is an inequation, we're actually going to get, potentially infinite number of solutions here. So rather than just 2 solutions, like with the equation above, we might get an infinite number of solutions. So let's think about our 2 cases here. Case 1 and case 2. Now again, you don't need to write this bit here if you're pretty clear on this. So 1 would be where the thing in the absolute value is greater than or equal to 0. Now the expression this time in the absolute value is just x. So when x is greater than or equal to 0, and case 2 would be where x is in fact a negative value. So in the case that x is greater than or equal to 0, taking its absolute value has no impact on it at all. The absolute value of x is equal to x when x is greater than or equal to 0. But when x is less than 0, we say the negative, or the absolute value of x is the negative of x. So then we'd be solving that equation there. Now you can see in the first case there, well, there's really nothing to do. That is the solution. So one part of the solution set is any value of x which is greater than or equal to 5 is going to be a solution. And the other one here, remember when we work with inequalities, here if I multiply both sides by a negative, I need to reverse the inequation sign. So to say that negative x is greater than or equal to 5 would be the same as saying x is less than or equal to negative 5. And for these ones here, we want to show our solution set on a number line as well. So let's draw a number line here. Let's say there's 0. Let's put positive 5 there, negative 5 there. Now, the first, from case 1, we're saying any value of x which is greater than or equal to 5. So anything greater than or equal to 5 is going to be part of the solution set. Now, if it was just x greater than 5, I would leave that circle sort of unshaded. I'd leave it as an open circle. But because the solution set includes 5, I need to colour that in just to show that 5 is also part of that. And then the other, from case 2, we've got x is less than or equal to negative 5. So that's colouring that in because negative 5 is included. That's all of those values there. So if we pick any value of x represented by where those 2 lines are, then taking its absolute value will give us something greater than or equal to 5.